Good evening, everyone. Today is our live session 3 for the course Optical Fiber Sensors, and I am a teaching assistant Ankur Kapre. Today I am going through the week 3 sessions where we'll discuss about the contents from the week 3 and also few questions related to that, and we'll be having some discussion regarding the doubts. Okay, so first I'll start from the optical receiver and receiver design and noise analysis things, where as we know that the optical fiber sensor or any kind of sensor will be having any kind of optical sensor will be having a photo detector where the photons will be converted into the current, and that current will be amplified later to generate voltage, and which can be converted to which can be digitalized using the ADC. So for the engineering of this detector system, we need to understand what are the things are involved in the optical receiver system, where the photo detector, and related to that photo detector there will be so many issues, which is like noise and gain, then bandwidth, then the speed, how much it can be, we can bandwidth, speed, and accuracy. Those things we need to take in care for, we should take care of those things to achieve the proper sensing using this optical in the optical devices, So first thing, we'll start from the photo detector. What are the things are there in that? Yeah, you can see here how photons are arriving. Let me check, somebody is joining maybe. Yeah, so you can see here that how photons are arriving to the photo detector, and it is converting into the photo current, and which we are having the noises. There are few types of noises already written here: short noise, thermal noise, dark current. Okay, so we are just looking into the issues which are associated with the photodiodes. Then we'll go for the next things. What are the photodiodes? What kind of amplifiers are there? Okay, so moving towards the first thing, which is the waveform, which is generating from the optical intensity. Once the photons are hitting on the photodiode, I don't know whether, yeah, you can see here how we are dealing with the photodiodes. First example, the exception, which is ideal. The waveform should be a square wave, which is generated by the photons which are hitting on the photodiode. Okay, but we have already discussed, like you have seen already in the lecture, that the photons arrives in a different time interval. Multiple photons will come in a first time interval, a unit time interval, then few photons will come for the next unit time interval, and that's how we will get such kind of noisy photocurrent based waveform, square wave. And in reality it is because of the so many things related to photodiodes characteristics. So uh, yeah, so at nanoscale the photon emission is stereostatic. Okay, then so as we discussed, the randomness in the arrival of photons is giving birth to the noise, and also we first quantify the chaos. Okay, moving towards the next thing, that short noise. What we have discussed about the different noises. Let me go through the notes, then it will be easy to teach you guys. Yeah. So, yeah. So as we discussed previously, that there will be first we'll discuss about the responsivity, which is for indium, gallium arsenide, or silicon. It will be, there will be a ratio of holes and photons, which is called Ka. For silicon it is 0.1, and for what happened? Something is problem. K is 0.5 for indium. I don't know what is happening in this. Gallium arsenide. So responsivity depends on the first thing, that M is the multiplicative gain M, and second thing is like the M. Actually the gain will be depend on this Ka, and there is formula we have discussed in the previous last week. And if we talk about the APD, so APD what it has is M, responsivity of APD is equal to M into R of PIN. So if you have the M in unit, M is equal to 1, then it will be, APD will work as a PIN, responsivity will be that much. And if it is multiplicative gain is 100 or 1000, then it will be that much responsivity will get from the APD. But associated with this, noise also will be associated with this. So the response time and noise will noise will increase with the responsivity, but the response time will decrease. Okay, so what we'll discuss now is the noises. What are the noises? What kind of noises are there in this particular photodiode system, and how it is affecting. So first thing is like there will be a short noise. It's mentioned here. The short noise arises because of the it occurs because of the random arrival of photons. So if you have a time window, if you divide in the different time window, suppose here 1 photon is coming, here 3, here 4, and here 2. So you can see that with the time, with respect to time, the photons are hitting to the photodetector is different. So that's why you are getting the short noise, and it can be the short noise variance, which is sigma square S or short, is equal to 2q in bracket IP plus ID into del F. What does it mean? It's like, the first thing is if you see the lecture, you will understand that these are the parameters for the short noise, and the ID is because of the dark current. What does it mean by dark current? So sometimes what happens that photodiode, usually not sometimes, has like tendency to generate hole and electrons without any photons, without hitting any photons, because of thermal excitation. So that ID is because of the thermal excitation, and we have included in the short noise itself. So this is a complete equation for the short noise plus dark current noise. Moving towards the next, which is the thermal noise. It's because of it's also says as Johnson noise, where it happens because of the random thermal motion of charge carrier in the resistor. So if you have a resistor, so what happens is you will be having um, uh, the variance sigma square thermal variance, which is related to the it's equal to the 4 kBT by RL and delta F. So you can understand that the kBT is playing a role in the thermal noise. If it is more larger the temperature, the thermal noise will increase. Also it can be reduced by using the low resistance in the circuit. So also with the temperature, if you reduce the temperature, the thermal noise also will be get reduced. But at the ideal room temperature, the thermal noise will be, if it is a standard if you have a standard line, so somewhere here the thermal saturation will be there. If you plot against frequency versus STF, so this will be around 2 kBT by RL. Okay, so it can be reduced by reducing the temperature. Now we'll discuss about the total current, no, total voltage which is coming, root mean square voltage, which has the all the noises included in that. Okay, so first let me check whether someone is there. Yeah. So you can see here all the noises in the current, which are short noise, thermal noise, and the amplifier noise. So all this will be, sum of this will be the total current variance, noise current variance. Okay. We have discussed about the short noise, thermal term, then op-amp term, which will be voltage density, which depends on the voltage density and current density as well. Okay, so total root means square noise is the root square of the sum of the independent variance. Reducing one source is futile if another dominates. Okay, so these are the total noise analysis which I am recapping here. Then we are talking about the APD advantages, why we are using the APD advantages, and how we are getting the gain, internal gain more compared to the PIN one. So mathematically the noise variance is directly proportional to the m square, the multiplicative gain. Then yeah, so for PIN diode the m is equal to 1, and for APD it will be more than greater than 1. It might be 10, 100, thousands also. So as we know that if you are increasing the gain, the noise will also increase because of so many whatever we discussed previously, those things, and also because there is randomly the ionization is happening because of the electrons. One electron is hitting to two electrons and generating electron hole, two atoms, or it's generating two pairs of electron and hole. Again it is hitting two, then it is a it's happening the multiplication, and that's how the APD works. And it's a very random process. One can hit one also and two also, or the hole also can generate the electron hole pair again. So it's a very random process, and that's how this it's a square of the multiplicative gain. Moving towards the next thing, which is the impact of K. As we discuss about the loss, how the noise is, the loss is correlated with the noise, or the waveform is deforming because of the noises. But we need to think about the Ka also. Ka is the ratio of the whole ionization of electron ionization. So previously we have already discussed in the last class that it is hole divided by electron ratio. Okay, so number of hole and number of actually NH by NE. So if you see in an indium gallium arsenide, which is we are talking about the APD only, so K is around 0.5, and you can see that at the optimum gain is approximately 20 to 30. It can be if you are dealing with the temperature, low temperature, because thermal noise if you reduce, then it can go up to 40 to 30 to 40 or 40 to 50, that much in this range. But if you are talking about silicon, the Ka is 0.1, and the optimum gain we are getting is 100, and it can be little bit more also if you are optimizing properly. Then how it is affecting the impact of K is affecting the total gain, or reducing the noise. So it depends on the equation, which is, let me check that equation, we'll write it. So we have discussed about this equation where the Fa is, let me write this Fa here, maybe the equation equal to, depends on the Ka m plus 1 minus Ka and multiplication in bracket 2 minus 1 upon m. So you can see here, if you are thinking about the Ka can be, if you are talking about Ka 0.1 and 0.5. Suppose we are keeping Ka as a 1. So what will happen, this particular part of the equation will become 0, 1 minus 1, 0, and Fa will become m. So it's a directly proportional, the noise variance is directly proportional to the Fa, and Fa, if it is equal to m, then if you are giving thousands of like gain, then noise variance also be that much, it will increase. So if you are giving Ka, if you are having the Ka is equal to 0.5, so what will happen, it will be both the places will get the if we keep here and here, then we'll have this kind of let me change the color. This particular optimum gain with a 0.5, understanding. Then if you have 0.1, then this part will be not dominating compared to this one, because here it will become 0.1, and because of 0.9, if you are multiplying with this much value, then or you can take as a K is equal to 0, so we can understand what is happening. This part will become 0, and this will become as a FA is equal to 2 minus 1 upon n, and if you solve this, it will become very high value with compared to m, and it's a m, if you are increasing, then it will be decreasing. Okay, so understanding, once we have one kind of criteria that if you are in Ka, the ratio of the hole ionization and the electron ionization, if it is very high, then first part will dominate, and if it is very low, then the second part will dominate. Okay, so we have understood about the APD, how the noise will increase with the multiplicative gain, and also having the problem with the optimum gain if we are dealing with the Ka. But the PIN can have more lesser noise and higher the wave function generation, but APD will be having better and better the response. Okay, you will get very noisy, but it will be with low current also, with very low photons also, it can generate it can sense it. Okay, so talking about the bandwidth of APD, because the gain we are thinking like we can get more and more gain in APD, noise also will increase. It can be also tuned if we are talking about the Ka value. Based on the material, we can tune the Ka, and based on that, we can have the less noise, and noise also can be reduced by number of time accumulation. So that is also the secondary now for a while. But the first thing is like bandwidth and gain. So if you are increasing the gain, let's suppose you are increasing the gain up to thousands time, then bandwidth automatically will decrease if you are increasing the gain. Okay, so it's inversely proportional. So it says that the design rule says that the trade-off high responsivity is equal to lower bandwidth, and that's how most of the APDs will not be having the higher speed signal generation. Just low gain, low bias for high speed signal, and high gain, high bias for weak signal. So if you want less noise, or you can say that more gain, and yeah, so for high gain, it should be longer the multiplication cascade. And the longer the multiplication cascade will also have the issue with the short noise because of the short noise, or we can say the thermal noise, which also uh, square m, it also depends on the m square. Okay, moving towards the next thing, which is the load line comparison for the direct load and TIA, trans impedance amplifier. So you can see that in load line, if you are using that photodiode with the load RL, so the V out will be having the slope of minus 1 upon RL. Okay, if you are um, um, having the plot, the plot against IP versus VD. VD is in a x-axis and IP in the y-axis. So you'll be having the load line like this kind of slopey load line. But if you are using the TIA, there, like if you are using just a second, let me check once. So so this excess noise factor, okay, it depends on the Ka. If you have Ka is equal to, suppose for TIA I am talking about, K is 1, so what will happen? This FA versus multiplicative gain will be having the straight line, something like this. If you are decreasing the 0.1, it will be like this, and if it is 0.5, it will go like this. Initially it will be slopey like this, then it will go like this, and there will be one baseline which is K. So yeah, so we were talking about the noises. Now we will talk about the converting current to voltage. First thing is that in the direct load, it will be having the problem with the load line, which is slopey. But if you are talking about the TIA, it will be having horizontal line. The flat load line is constant VD. Okay, so if you are using the RF here, then the virtually it will be in the ground state, like 0 volt, and will get the V out at a constant VD, diode potential. Okay, moving towards the second thing, if you want to having the increment in the sensitivity, to increase the sensitivity need large RF, and to increase the speed, smaller RF value should be there. For constant, the gain bandwidth product GBP of the open. Okay, so if you are introducing here the capacitance, so it's like a limitation, it will be decrease the bandwidth if you are increasing more and more capacitance, but the gain will be increased. Why the gain is increasing here is because you are having V out voltage. If you want to increase, so it is inversely proportional to the CF. Okay, so that's how you are increasing the the amplifier is increasing the voltage V out, but also decreasing the bandwidth. So here two kinds of op amps can be used. One is BJT and second one is FET, FET, and examples are given here from the uh, classes itself. I have taken these examples: OPA 846 and OPA 657. You can see here that what are the pros for the BJT input, where it's a high gain bandwidth product, excellent frequency response. Okay, then cone is what? High input current noise density. It's in a picoamp per root hertz. Okay, while talking about the FET, it is having extremely low input current noise density, which is in femtoampere uh, per root hertz, and typically low bandwidth it has. So if you see the plot, which is frequency, the bandwidth, frequency versus gain. So for BJT it will be look like this, up to 1, 10, 100, 1000. Okay, for FET it will look like this. So BJT, and this is for FET, can clearly seen that it requires the gain can be increased with the FET up to few thousand but the frequency it will deal with is 150 megahertz, while the BJT will be having 300 megahertz frequency. You can see in the example. So in optical receiver design, the input current noise is usually dominant factor. FET wins in the on the sensitivity. So if you want bandwidth, you can go for the BJT op amps, or if you want the sensitivity, then FET is best for that. Also, the sensitivity depends on the delta output upon delta input, which is output current, which is dy by dx. Okay, so if we see this is the noise floor, which is minimum detection limit. So this is how we can detect the output current based on the input, which is for the sensor work. Here what we are giving as our input is the gas concentration. Suppose ammonia NS3 in ppm. If you have ammonia's concentration increasing, then the current will also increase, but after some time the saturation will happen. If you are increasing the ppm more, then the output current won't increase, and that's what called the saturation point. Also there will be a detection, the minimum detection limit, which is called a noise floor, where below that ppm you can't detect. It will the current output current won't have that much sensing capability to detect below the few ppm values. So the detection or sensing application of the gas will be having the certain range. It can be from 10 ppm to 100 ppm, something like that. If you increase to 1000, it will not work. If you decrease below 10 also, it will having some problem to detect accurately. Okay, so sensor performance matrix depends on the measurement range where it is having the operation range, then sensitivity, the gain of the sensor, which is a slope. If it is having the sensitivity, it's like a the increment on the output current compared to voltage, compared to the gas concentration. That's how we deal with the sensitivity. Then response time, how much time we require to sense that. It is not perfectly can be done with the one accumulation, so we need to go multiple times. So time to settle that, and it will take few seconds to understand that how much concentration of gas, suppose ammonia or any another H2S, those gases are there. So it will take a little more time. Now we'll discuss about the sensors which is having the precision and accuracy requirement, because any sensor which is working for this kind of application, optical sensing or either normal sensing, which should be having the accuracy and the precision as well. So you can see here 4 examples how the accuracy and precision has been shown. First example, you can see that this is your your target is here in the middle. Let me change the color. Where is that? Your target is here. What is this? Here in this place, and the accumulated data are in surrounding but very close to it. Here, this near to that, and also the averaging value is coming to this point only. So it says that the accuracy and the precision is very high for this. If you are talking about the accuracy and precision for the second image, where you can understand that this is the target point, we should achieve that the measurement here. But what is happening is like it is a concentrated, but it's concentrated somewhere else, not at the target point. So it's a little far from that. Okay, so what it says that the accuracy is very low, but the precision is very high. So sensor is working fine, but it's not having the calibration. Second one is accuracy is high because there are points, certain points outside, inside, here also, but the averaging, if you are doing average, so all are coming to this point only if you are doing the average. Okay, but it is scattered, so precision is very low for this sensor. For example, if you are using as a sensor to detect it, so the precision is low but accuracy is high. The last one, you can see that everywhere the randomly points are coming, and it's not near to the target also, and it's also not averaging out to the target. So for this, the uh, spectra, or we can say that average plot against probability versus measurement value will be like this, and your target value is in the middle of that. But if you are talking about here, your target value was here, but you are getting the value here, but very sharp. Here what is happening, you are getting the target value achieved, but it's not concentrated, so it is like in this way it will come. So this is the probability, and this is the measurement value. Here it is totally different, might be here somewhere it is coming, the average value. So target value is here, but your average is coming somewhere here, this place. So you need to calibrate after dealing with the noise, then dealing with the gain and bandwidth. You need to calibrate this sensor for the sensing application, which has few more problems, which are, first thing is like calibration. Second thing, it should be having the accuracy, which can be it should be, with the calibration we can improve the accuracy, but the precision we can improve by averaging out. Suppose you are taking one time accumulation, so it will be not that much great if you are comparing averaging out to 10 times. So your value you are getting closer and closer, that's how you need to average it out. You can see here also multiple data points are there compared to one data point. So sometimes because of some noise issue or some kind of defects, maybe it will change the value, but if you are doing multiple times, it will be calibrated. Okay, so accumulation also helps in this case. Here we are talking about the cross sensitivity and environment interference. Your sensor is working fine now. You have calibrated, you have accumulated multiple times, the data has been taken multiple times, you have improved your gain and bandwidth as well. Also you have reduced your noise with reducing temperature, whatever we had discussed previously, also using some kind of parameters or op-amps, choosing selective op-amps. While talking about the sensor response, it comes to the gas concentration we are talking about here in a ppm. If we talk about that, the material which is like a molecule, gas molecule, ammonia is our target, but it also can interfere with the hydrogen and carbon dioxide also. If you have tiny amount of or few ppms of hydrogen, it will also make some problem to detect the ammonia, and this is an ambiguity problem where a reading of 200 ppm could be ammonia but a hydrogen leak as well. So for that, the sensor do not exist in a vacuum, and you need to, what is written here is robust design requires characterization, false positive and interfering agent in the development environment. So you are capitalizing the sensing for ammonia, and you are getting the interference from this also, hydrogen also. So it's like after dealing with the sensitivity and everything, we need to deal with the environment also. So this is called a cross sensitivity, and we'll discuss about this one in a later classes also, how it is affecting. And here I have shown the art of the trade-off. So if you want to increase the bandwidth, you need to trade off with the precision and sensitivity. Similarly, if you want more sensitive sensor which can have more gain, you need to trade off with the bandwidth and precision. Again, if you want precision, then you need to deal with the sensitivity, and you need to compromise with the sensitivity and the speed. So best thing is the average of those all three uh, uh, parameters: speed, sensitivity and precision. If you have, you can't achieve in the center, but if you have something here in this area, it can be a good sensor. So if you can understand that. So in summary, I would say that noise is fundamental. We need to fight with noise and thermal flow. And noise, I told that how to reduce it. Also um, thermal flow, how we can with the accumulation or more number of times collection can reduce the thermal flow. And um, gain cost bandwidth. So anyhow, we need to, the tiny amount of signal which is coming in the reflection geometry or any transmission geometry, the signal should be having more gain, and we need to deal with the bandwidth. Third thing is linearity versus speed. So if you are going for the PIN, and you can have speed, but you will not be having the gain. So you need to deal with the linearity and speed as well. So TIA are limited by the op-amp GPP. Okay, so in that case, so we need to deal with the TIA then. Then after that, calibration and averaging will come into thing, and which will take care about the precision and accuracy. But anyhow, in the end, the sensor should work with a particular work which for which it has been designed. It is designed. So there is no perfect sensor. There is only the optimal measurement of the constraint for the specific application. This is the final thing about the recapping of the week 3. Now we'll move towards the question answers. We'll discuss about it. So are you able to understand whatever I have discussed here? If you have any doubts, you can ask me. We'll discuss in detail if you have any doubts. After that, we'll go for the question answer sessions. I think I recapped it properly. Maybe if you have anything it is missed, let me know. Do you have any doubts, Janani?
No, sir.
Yeah, if you, I think you have covered it properly. Maybe that's why you are.
Yes.
Yeah, very nice then. Very good. So let's move towards the questions then. We'll discuss. You also solve. I'll ask few questions to you, and we'll see how much you understood this topic. So give me 2 to 3 minutes. I'll just come back, and after that we'll discuss. Okay?
Yes, sir.
Sure. Let me have water. Okay, so let's discuss about the question answers. So first question is, according to the McIntyre model for avalanche photodiodes APDs, what happens to the excess noise factor Fa as the multiplication factor M increases if the ionization ratio rate ratio Ka is exactly 1? Can you just let me know what could happen with the Fa? Are you able to follow? I think you have seen that equation, whatever I have written. Fa is equal to Ka M plus 1 minus Ka in bracket 2 minus 1 upon M. If K is 1, exactly 1, then what will happen to Fa? Janani, please tell.
Yes, sir. From the formula,
From the formula.
Fa and M are linear relevant.
Very good. So, if you are keeping 1, K is 1, this part of the equation will become 0, and here if it is 1, then Fa is equal to linearly it will be related. So if multiplicative gain is increasing, then Fa will increase linearly with M. So this is the correct answer, correct journey. Second question is, a designer uses a trans impedance amplifier and decides to increase the feedback resistor RF to improve the gain. What is the primary trade-off regarding the noise and bandwidth? So just check and let me know what could be the answer for this, how we will deal with this noise and bandwidth. What will happen? Let me know.
Bandwidth and noise both increase.
So you are saying that if you improve the this one you're talking about bandwidth and noise.
Yes.
Yeah. So in the direct load configuration, what will be there? Oh, I changed the question. Oh, yeah. So both the bandwidth and the noise will increase. That's correct. Moving towards the next question, which is which of the following best describes the direct load configurations limitation compared to the trans impedance amplifier? So options, please let me know what could be the answer for this. Let's tell me what could be the answer. This is definitely not correct. Direct load configuration generates zero thermal noise, which is not even possible. First option C, the direct load configuration allows for the vertical load line maximizing current extraction. It's not exactly correct because it's not a vertical line. Will it be vertical line?
Sir. No, sir.
Yeah. Then C, you see direct load configuration has higher bandwidth due to the absence of op-amp. Is it correct? And B says that the
Not sure, sir.
then deal with the B. The load line is slanted, causing the development photovoltage to reduce effective reverse bias and limit the current. Will it be? Which is the limitation for the direct load? We have seen that it is slanted. So if you compare these two, B and C, which one you are thinking like it's not limitation for the direct load?
A slanted line. B, option B.
Correct. Because there is no in the direct load we are not using the op amp. Anyhow we are not getting the gain, but also we are getting higher bandwidth. So this is also not limitation. So this is the limitation for that, and this is the correct answer for that. Moving towards the next question, which is mentioned here. For an APD made of indium gallium arsenide with Ka, which is equal to 0.5, what is the typical range for the optimum multiplicative gain mopt?
10 to 20, sir.
10 to 20. I think you must have visited the lecture. So this is the correct one. Okay. If you are keeping all the values 0.5 in a multiplicative gain, you will get this value 10 to 20. What is the equation for this? Let me check the equation right here. Okay, leave it there. To write so much here. Next question is, in sensor performance matrix, how is precision or repeatability distinguished from accuracy? So precision and accuracy, how it is distinguished? Let me know for this. Precision is the slope of the calibration curve, while accuracy is the response time. Option B says accuracy refers to the smallest detectable change, while precision refers to the measurement range. C says precision refers to the bunching of multiple measurements, while accuracy refers to the deviation of the mean from the true target value. And D says accuracy can be improved by taking more measurement, while precision can only be improved by calibration. Let me know what is the Correct answer here?
Option C.
Hmm.
Precision multiple measurements.
Multiple measurements, yeah. And accuracy refers to the deviation of the mean of the from the target value. So yeah, so option C is the correct one, where accuracy can be improved by um, calibration, and precision can be improved by multiple measurements, multiple accumulation of data. Moving towards the next question, what is the effect of increasing the multiplication gain m on the 3 dB bandwidth of an APD, avalanche photodiode? Let me know. A says the bandwidth remains constant regardless of the gain m. B says the bandwidth is only affected by the feedback resistor RF and not the gain m. The bandwidth increases because the higher current speed up the carrier transit time, and D says the bandwidth decreases due to the avalanche process takes a finite amount of time to cascade. So how multiplicative gain affects, like increasing in the multiplicative gain increases affects the bandwidth. If you have PIN photodiode and APD, which will be having higher bandwidth?
APD, I guess.
Bandwidth.
Bandwidth.
Bandwidth means you can say frequency. How much?
Bandwidth means frequency range.
Range.
So more gain means more bandwidth.
No. Did you understood the concept of bandwidth? Let me write the equation here. Bandwidth. Where is that? We have discussed about the bandwidth. Yeah. So the relation here is like this: A naught open loop versus frequency. So if you are having the GBW, if you see, it will be constant, okay, then GBW by frequency limit, and it will decrease. You're understanding? If you are increasing gain, it will decrease the frequency.
Increase frequency, it will decrease the gain. Okay, sir.
Are you understanding what I'm saying? If you are using the APD, it will take time to happen the multiplicative gain. Okay, one electron will hit and it will generate one electron hole pair. Then same it will be having multiplicative. It's like a multiplicative process. It's like a chain process kind of thing. So what is happening? It is taking time, and that's why reducing the bandwidth 3 f3 dB, increasing the uh, gain, APD will increase the gain but decrease the bandwidth. So now you tell the answer, what is correct?
Yes, sir. Option C.
Hmm.
Bandwidth increases.
So there will
Sorry,
be
sorry.
bandwidth restrictivity in TIA every time.
Yes, sir. Option D. Sorry.
Option D. Yeah, yes, that's correct. Maybe I can more properly, I can explain you. Let me check once. Where did I write these things? So response time you can understand here. F3dB is equal to 1 by 2 pi m naught tau e. So here m is the gain at 0 frequency. Okay, and if you see for the PIN, m is equal to 1. If you for your checking for the avalanche photodiode, either it will be, it will not, either it will be 1 or greater than 1. So you can understand that the bandwidth will decrease if you are increasing the gain. So here it's mentioned already, increasing the multiplicative gain. So how it will affect the 3 dB, f3 dB bandwidth. Now you understood what I'm saying?
Yes, sir.
Okay, good. Moving towards the next question. If an optical sensor specification sheet mentioned cross sensitivity to hydrogen in an ammonia sensor, what does this primary qualify? First option is the ratio of hydrogen to ammonia that the sensor can measure simultaneously. B. The uncertainty introduced into the ammonia reading by the presence of hydrogen gas. C. The speed at which the sensor switches from measuring ammonia to measuring hydrogen. And D. The increase in the sensor's lifespan when exposed to hydrogen. What is the correct answer here? We are dealing with the cross sensitivity to hydrogen for ammonia sensor.
Option A, but doubt with B also.
Cross sensitivity, what you understood with the whatever taught you, cross sensitivity is not to measure simultaneously anything else. The sensor is made for the ammonia to sense the ammonia in ppm level. If you have hydrogen, it will also make some kind of problem. It's called cross sensitivity. It's it's sensing ammonia, which is for that it made to sense the ammonia, but also it is sensing hydrogen as well. Now you tell your answer. So I'll just put the wrong here, okay, so you'll understand. The ratio of hydrogen to ammonia that the sensor can measure simultaneously. It can't measure because hydrogen we are not the optical sensor for ammonia is standardized, but for hydrogen it is not. And if it is happening together, then it will make problem for ammonia sensing. Now you understood what I'm saying?
Yes, sir.
So what could be the answer now?
Option B.
Very good. So uncertainty introduced in the ammonia reading by the presence of hydrogen gas. So you made a very good sensor. Everything you have taken care from the optics part and designed nicely the receiver, but source also everything. Then in the end you are dealing with the sensing, and there the external thing is making the problem during the optical sensing. It's like a cross sensitivity. Suppose you have ammonia gas you are measuring somewhere in some chamber, and suddenly there is increment in the hydrogen sulfide, hydrogen, or ozone, carbon dioxide. Those things also can affect the optical sensor accuracy, or we can say precision. Both also. Mostly the precision. So it will increase more and more number of um, uh, we have one plot which is dealing with the probability versus measurement value. So probability density will increase unnecessarily without having anything, without knowing that hydrogen is there. So that need to be uh, deal with during the cross sensitivity. Then last, I think this is last question. In a TI design, the 3 dB bandwidth is given by f is equal to 3 dB. F 3 dB is equal to under root GBW divided by 2 pi RF in bracket CF plus CD plus OA. Now, if a designer wants to double the bandwidth without changing the op amp and or capacitance, how must how much how much RF be adjusted? Let me know how much we need to adjust RF to double the bandwidth. Any doubt? Any answer you have?
Now, RF also increased by a factor of.
By a factor of?
Sorry, sir. Wait.
you need to increase the bandwidth. So RF should be increased or decreased?
Decreased.
Yes. Now you tell. Double, you need to increase double time. So what you need to do with the RF? How much we need to reduce it? Suppose you are using 1 mega ohm. So 1 mega ohm, how will do? Suppose 4. Oh no, not to confuse with the numerical thing. Otherwise, it will be difficult. Okay, just tell me. Understanding? It's an under root, so you can see anything. You just tell me. Two reduced value are there, this one and this one. Anything you tell.
1/2.
Now F3 dB is equal to whatever it is. Okay, I am just writing it's proportional to under root 1 by RF. You want to increase the its bandwidth to 2 times. This side also 2 you need to take. Now 2, if you are taking in under root, how it will be? Let me write properly, it is not looking good. Just a second. If you have 2 F3 dB, so under root 2 you need to write like this. Understanding what I'm saying? RF, take this value inside, so it will become 2 to the power 2 divided by RF. And what does it mean? You need, if you are making it like this, RF, let me write properly, 1 divided by RF, which is also divided by 4. So how much time we need to reduce it? Did you understand what I made? Double if you want to do the bandwidth. So you need to reduce 4 times the RF. This is the correct answer for that. Are you understanding what I'm saying? Other things you need to keep constant. CF, CD, OA you can't change because it's already mentioned here. Designer wants to double the bandwidth without changing op-amp and capacitance. So you need to change obviously RF. So 4 times if you reduce, then the bandwidth will reduce 2 times. 4 times if you reduce the RF, bandwidth will increase 2 times. Okay, so yeah, if you have doubt, you tell me, ask me.
Yes, sir, understood, sir.
Anything else you have doubt, let me know. I'll be here for another 20 minutes. I'll keep live. If you have not understand anything, or you want to discuss with professor anything, so I can convey the message. You understand on those things? This why this is noisy, this area. In reality, why we are taking the getting the photo current in this way?
Yes, sir, because of noise, types of noises.
And if you want this kind of thing, what you need to do?
Reduce the noise.
How you will reduce the noise? Uh, One of the best example, like how we can reduce that. How you improve the sensitivity of sensor. You can collect multiple times the same place. Are you understanding what I'm saying?
Yes, sir.
If it is a um, repeatable movement, you need to collect multiple times. So this kind of noise, the random arrival of photons, will be averaging out. Where it is low, it will be average out to medium, and the average out, and the high also will be average out. So you will get almost this, not almost actually, it will be having a noise because of the thermal and other things also, but anyhow you can at least recover the, or you can uh, accuracy, precision you can improve with that. Not accuracy you need to tune it, you need to calibrate it. So understood what you need to think about for noise. First thing is like you can reduce the temperature, so little bit it will decrease. Okay, because here you see thermal is directly proportional to the noise, temperature is directly proportional to noise. Then dark current you can't, you can, but it's already this dark current also depends on the temperature. Then short noise, random arrival of photons, how you will get rid of it? Averaging out. Then apart from that, accuracy, how you will improve? Calibration. Precision, number of time, collection, data collection. Okay, bandwidth, if you want to increase, then you need to compromise with the gain. It's a inversely proportional, you can say, not directly proportional. You can see here gain is inversely proportional to the bandwidth m. And to improve the gain in TIA, what you need to do? Anything? If you want to improve the gain in TIA, you need to increase the RF, and it will increase the gain. But if you want to, it will decrease the bandwidth. Let's write shortcut 3 dB at 3 dB. It will decrease. Then capacitance also will decrease the bandwidth. You can see the equation here. It will increase the gain but decrease the bandwidth. Okay, then any doubt you have, you just ask me. Okay,
Yes, sir. We have problems in assignment 3.
what's the problem with you? What's the problem you are dealing with? question number. Tell me the question.
Can we solve question number 7?
No, actually I can't solve, but I can give hint because you have it's live, I think, or it's finished already. Still you need to finish it, huh?
Okay.
Yeah, once, because it will be like, if I'll tell you, wait, I'll check once. I don't know why it is not opening. Yeah, done. Question number 7 you are saying. What do you have problem in this? For the above system we need to maintain a signal to noise ratio of 10. The minimum incident power should be. So you can reverse calculate the power. What's the problem in this? You have photodiode. Where is that? Okay. Detector is there, everything is there. First, if you solve the first one, then you'll get the SNR. Okay. Question number 5. No, is there any relation with this? Just a second, let me check. For the above system, okay. Six to 8. Gain PDC. You need to calculate the power, which will be in microwatt or milliwatt. I don't know, milliwatt it won't be, microwatt I think, or nanowatt. Photocurrent, then voltage, where it is. Okay, once you finish the assignment, the date, if it is after the date of this completion, I will go through it, okay, and we'll discuss in the next session, because if I will tell you, then this is not correct way then.
Yes sir, understood.
Let me check that. Even you can check the equation. Are you not able to follow that equation? First question, did you check the question number 5? It's working for you? You have power, you have wavelength. You need to do just opposite to that. Question number 5 is opposite. There you are calculating
Okay.
SNR.
I'll do something.
There you are calculating SNR. You need to calculate here power. That's it. Okay, then I'm closing today's live session. Then we'll discuss in next week. Properly we'll discuss and understand. Okay.
Okay, sir. Thank you.
Yeah. Thank you so much for joining.